Alrighty, okay. So we're going to begin the video today with aldehyde chemistry. And in particular, we are going to be investigating the reactivity of the carbonyl group itself. So that is the C double bond O moiety. So this is following directly out of Klein 3rd edition. This is chapter 19 material. And most of the pictures and things that you see in here are directly copy and pasted from Klein, and I've made notes in the places where I can. Okay, so let's start. So we are concerned today, again, with aldehyde chemistry. How can we react it? And in particular, we want to know what's going on with the carbonyl group. Okay, so as an introduction, okay, we all should recognize at this point what an aldehyde functionality is and the difference between an aldehyde and a ketone, both containing the carbonyl group, or that is a carbonyl moiety, so that is obviously indicated by a C double bond O. And there are many derivatives of carbonyl functional groups. You have aldehydes, you have ketones, you have carboxylic acids, and you have esters. So those are all derivatives of the carbonyl moiety. The two that we're most concerned with currently are aldehydes and ketones. Aldehydes, interestingly enough, play a very big role in flavors popping up in places. You can even see here that we have a ketone, our carbone. That's what goes in most gums. Okay, a lot of you have used vanillin before with baking. We then also can see that ketones are very proactive inside of our body. So we have progesterone, and for us men, you can see we also have testosterone. The ketone here being the precursor to the name testosterone. Okay, so progesterone, testosterone. Okay, or even as I mentioned in chapter 12 and 13 with the alcohols, we have estradiols. Ladies, that's for you. Okay, so that's just a quick introduction. This is some nomenclature. I'm going to skip it in this video, but it's important that you begin to recognize what formaldehyde is, acetone, acetaldehyde. These three pop up quite often in synthesis, and they're usually, some of them here are used as pretty good solvents in reacting reagents. In addition, you should try to know or try to recognize acetophenone and benzophenone. Okay, the "-one at the end indicating that you have a ketone molecule. Okay, so we're going to go ahead and skip the naming here. It's mostly trivial, and I've included some practice. At this point, you should recognize how to complete all of these transactions. So given the starting molecule, you should be able to get to the final product. So I encourage you to stop the video now and provide the necessary reaction conditions in order to get those products. Okay, and then we'll go over that in just 1 second. Okay, so you should have been able to do all of these because all of this chemistry is vital. It is absolutely necessary that you know it so that you can do the aldehyde chemistry. Okay, so we have an alcohol here. It's secondary, and in fact there is one free hydrogen right here, and so that lets me know that I can do one oxidation on it. So this is clearly an oxidation reaction, right? We gained an additional bond to oxygen. So this one is level 1, this is level 2, and so we can put this in chromic acid. We could use sodium dichromate in an acidic environment. We could also just use PCC, namely pyridinium chlorochromate, but we went from level 1 to level 2, and because we only had one hydrogen here attached to this carbon, we could only perform one oxidation. With this molecule over here, okay, we clearly have a level 1 alcohol, and it has 2 free hydrogens, which means that it can perform 2 oxidations, that is, increase by 2 levels. So it's at level 1, and we need to get it to level 2. So we're going to prefer to use PCC here, pyridinium chlorochromate, because it isolates it at level 2, and we don't form the carboxylic acid. We cannot put this molecule inside of chromic acid because it would form the carboxylic acid product. So PCC is a good use here. Let's look over here at this reaction, okay? Some may recognize this reaction. I'm going to skip this one here, and I'm going to skip this one here, so D and C. These are from Chapter 8 and Chapter 9, and I encourage you to go look at them, okay? And you will find out something new. It's beyond the scope of our discussion here, but I encourage you to check out Chapter 8 and Chapter 9, and in particular, just look at the end of chapter review reactions. It'll only take you 1 minute, and I provided the book online, okay? But you may have some derivative of hydroboration oxidation in these such reactions. With reaction E, we clearly have broken this double bond and formed double bond O's in place of this double bond. So this is simply an ozonolysis reaction forward. So this one's an ozonolysis reaction. A and B are with PCC. D and C here, I'm leaving for you to go and find out with Chapter 8 and Chapter 9. And then F is a reaction which you recognize from aromatic chemistry, and it is clearly the addition of a acyl group. So this is Friedel's Kraft acylation. So you should have been able to get all of those. Okay, so I suppose that we can cut all the talk and just make this very straightforward now. We have the carbonyl functionality here, the carbonyl moiety, okay? And with resonance, we can really show it to look like this. So we see that there's clearly a region which is very electron rich and a region which is very electron deficient. By the same hand, we also have an inductive effect. So there's two different effects going on here. And when we look at the inductive effect, we can see that the flow of electron density through the sigma bonds clearly is moving towards the oxygen, okay, just due to electronegativity. So this partial positive character on this carbon, the partial positive character on this carbon indicates that it's a very reactive position, and in particular, it can be attacked at this position. It can be attacked at this position, okay, these are the same thing. Whereas up here at the very electron-rich region, it is very likely to attack something. So the positive part, this partial positive character, is likely to be attacked, and this oxygen is likely to use one of its lone pairs to attack something, okay? In addition, if there is a ketone functionality, both R groups are going to contribute to this partial positive character, or that is that they are going to combat the partial positive character because they are donating density into this this sink right here, right? This partial positive region. So it's a little less partial positive at this carbon when you have ketones. With an aldehyde, it's more positive because you only have one R group that's able to donate. So these R's are giving their electron density into that carbon center to make up for what was lost here. So those are just some things to recognize. But what we really want to start thinking about the carbonyl moiety as is this. Okay, so we're going to sort of ignore the top part. We've already seen this with Grignard reagents, and we're just going to look down here at mechanism 19.2. And what we want to notice here is that, as we have just seen, this oxygen, which is very electronegative, right? It will use its lone pair to snatch off a proton on some kind of acid, and in the process, it will form a negative charge on whatever A is. Now, you will see that once it snatches off the proton, okay, the region of partial positive density, right here, is likely to then be attacked, okay? And in the process, in order to annihilate the positive charge here in the oxygen, we're going to resonate up the pi electrons onto the neighboring oxygen. So through this arrow pushing, we're essentially going to be able to create a much, much more stable molecule. Okay, so with acidic conditions, what you should recognize is that oxygen gets protonated, the carbonyl's oxygen gets protonated, and then you can see that we can then perform a backside attack with whatever the nucleophile is, and that's probably an A minus, okay, or an A without charge. So we can also then investigate the resonance structure. So we're just looking at the first step here, but what we realize is that the carbonyl's oxygen was protonated, and instead of showing something attacking it, let's just show the resonance structures of this intermediate, okay? And we see that it looks like this. Now, oxygen has no charge, so he's all good. Hydrogen, no charge. These outside carbons have no charge. The one site of reactivity in this molecule is right here at this sp2 hybridized carbon, okay? It's a sink. It has high partial positive character, and so it's likely to be attacked right here, which means that something is going to attach itself at that carbon. And so we can think of this as a very powerful electrophile. Okay, this is a very, very reactive molecule right here. Okay. So let's I suppose that we could probably skip forward and look at this acid-catalyzed hydration. So whenever we're given arrow mechanisms like this, and there will be much larger ones to come, what we want to do is take it one step at a time, but we want to do an analysis of what happened right at the beginning and what did we end up with. And we can see that from our starting molecule to our end molecule, it's almost as if these bonds right here were broken up into single bonds and they were turned into hydroxy groups. So just given hydronium and formaldehyde here, let's say, okay? Let's just say that we just had formaldehyde and hydronium. We know that it's going to get protonated, right? Clearly, it's going to snatch off one of the hydrogens because this guy's an acid. He wants to give his hydrogen away. So the carbonyl's lone pair here, the carbonyl's oxygen's lone pair, snatches off a hydrogen and eliminates a positive charge. And we end up here at step 2. It's at this point that we've just seen that obviously the oxygen isn't going to attack the oxygen. We can get rid of the positive charge here simply by resonating up one of the pi bonds. In that process, a positive charge forms at this very reactive center, and this is where the deprotonated hydronium goes to. So hydronium gets deprotonated, and then the water, which it now is, right? This is protonated water, is now just normal water. It attacks at this very reactive carbon, and it attaches itself here. So we end up now in this intermediate. It's at this point that the most logical thing to do would be to just have another water molecule in our reaction flask rip off the hydrogen, and so it eliminates that charge. Now, what is important to notice here is that everything is in equilibrium. Okay, so if you ask yourself at every single step what's the most logical thing to do, this would be the series of steps that one would take. Okay, so what's important to take from this is that this oxygen gets protonated, okay? Never protonate this carbon first. Don't protonate anything on the outside. It is the oxygen which takes a proton in acidic conditions, and then whatever that reagent is, it's going to attack this carbon center right here. That is what is so important to realize. So we now know a new reaction. Given this carbonyl, if we put it in acidic conditions, it will split it, and we term this acid-catalyzed hydration. So it sort of splits this guy, and we still have the hydrogens. It's just that we earned a geminal diol in the process. So geminal diol, that is geminal, like the Gemini star twins, so they are at the same carbon, that's geminal, and we have 2 alcohols. So we have a geminal diol product starting from a carbonyl moiety. Okay, so let us generalize this a little bit more, so we're going to extend the definition now. So we have just seen that given water in an acidic environment, which is really hydronium, we can form a geminal diol. But what about if we wanted to form from the carbonyl moiety a geminal alkoxy? So that is an O attached to some carbon group. So we want to form this geminal alkoxy group. Well, it's quite simple. You simply just need a derivative of water. So instead of HOH, which would be water, let us say that we now want to use methanol, which would be CH3 in the R place, and then OH. So let's say that we use methanol. If we use methanol in an acidic environment, what we are going to get is a protonated methanol. So this is a new type of symbology that we're going to introduce here, and I'll show you it on my piece of paper. But this new symbology looks like this, and so we have our H of the plus, and this simply just means in an acidic environment. In an acidic environment. So this is a new type of symbology, okay? This is not, okay, it is not bracket H. Bracket H means reduction, but a bracket H with a positive in it means in an acidic environment. So there is a major difference between these two things, but we are particularly interested in the in an acidic environment. So what we just had, if you recall, we had ROH and then we had some arrow. It may have been an equilibrium, but it had this H plus. What this really means is that your starting material, which is this alcohol, it's this water derivative, really is protonated. So what this actually means right here is this. It means RO and it is protonated. This is what it really indicates. And you can see now that this looks just like hydronium, except one of the hydrogens has been replaced with an R group. So this is how we get that alkoxy attachment instead of the diol end product. Okay. So if I had water in an acidic environment, you see you can sort of just read this. If I had water in an acidic environment, I just protonate this guy. And so that would be hydronium, as I just demonstrated. Okay? So this is very, very important. This, if anything, this above this line right here is the most important thing you can take away from watching this video. You have methanol, ethanol, propanol in an acidic environment, and it will be protonated. And so fry this in your brain. Okay, we just saw hydronium here, but let's say that one of the hydrogens was really an R group. So now we're looking at it of this form. So we have protonated alcohol derivative form here. If this is the case, okay, then we can clearly see that from protonating this methanol, ethanol, whatever alkoxy group you want, we can end up with, instead of geminal diols, geminal alkoxy substituents. Okay? Now, let us look at how this proceeds forward. Okay? So we're just going to speak about this for a moment. I leave it up to you to study this mechanism, but I want you to understand the principle of what is happening here. So let's just see what Klein has given us. He states that in an acidic environment, okay, this carbonyl's oxygen will be protonated, and then this alkoxy, it's this alcohol, it's this water derivative, attacks the partial positive carbon center like we just saw, and it resonates up a pi bond in order to get rid of the positive charge. Okay, so let's just look at these first two steps. Now you may be thinking here, what is H-A? I mean, is this hydrobromic acid? Is this hydroiodic acid? Well, Klein does not do a very good job here of demonstrating what this is, but I'm going to show you it in a more suggestive manner. So, allow me to redraw the first steps here. So I will reconstruct these first steps here. I can straighten out my piece of paper. And what we have is we have this carbonyl, and then we have HA. But allow me to write HA instead as H-OH with an R group. This is what they really mean. What they really mean is that A plus is just OHR. And this thing has a positive charge. That's what they mean by A. So whenever they say H-A plus, they really mean him right there. They really mean this whole guy. So this is what you're looking at. You are simply looking at ROH in an acidic environment. You're looking at this guy. This is what they mean by the HO or the H-A plus, okay? So this is H-A plus. And you can see that clearly it's like water. It's like hydronium. It's just going to protonate that carbonyl right there. So he simply rips off a hydrogen, and in the process we can get rid of that positive charge. It's at this point now where this guy looks like water, but one of the hydrogens has been replaced with an R group. So after we perform this arrow step, just simply protonating the oxygen, everything becomes self-evident. So we are left with this now. And you should take a moment to look at what happened between the first step here and what we ended up with. We simply protonated this guy, and we ended up with the water derivative. It's just water, but one of the hydrogens is replaced with an R group. And it is now as simple as recognizing that this is very partial positive right there. Very, very partial positive. And so what's going to happen is it's just simply going to attack this carbon right there. So let me draw this again. Simply going to attack this region of partial positive density and get rid of the positive charge in the process. Okay, so that's all that we really need to know about this mechanism in order to write out the rest. So let's go back here and let's look at this mechanism. So we protonated our ROH group, right? We had ROH in an acidic environment, that's this guy. And then ROH, which is, right, it's no longer protonated, it's what we just ended up with, attacks this carbon center, okay, and resonates up the pi bond. And then remember, we need to get rid of this hydrogen. And so another ROH that's not protonated simply takes that hydrogen and it's in its protonated form again, and you repeat yourself, okay? This is how we get to our what we will now define as an acetal product. So I won't really call it a geminal dialkoxy product, but I'm going to call it an acetal, okay? That is where the carbonyl has been split into two separate bonds, two separate sigma bonds with OR groups, okay? This is also some other kind of geminal ether formation here. Now, what's important to take about this is these first couple of steps, and then recognizing that we have a functional group here at the midpoint called a hemiacetal. So we're halfway to making our acetal. That's one is an OH, namely a hydroxy group, and the other substituent is going to be this OR group right here. So the acetal is the geminal dialkoxy, and the hemiacetal is a hydroxy on one side, and then an acetal, half of the acetal on the other side. So that's important to distinguish hemiacetal and acetal. Okay, so we can generalize this and ignore mostly what's in this slide. I'll leave you time to go back and look at that. But if you have, let's say we have ethanol, so ethanol is our R group, and we put ethanol in an acidic environment, we really have protonated ethanol, and it does all this hand wavy stuff, all this magic, and in the end you just see that the carbonyl is the only thing that changed here, and it changed to two of the OR groups. OET. OET. Can you see that? So ethanol in an acidic environment will split a carbonyl up into two separate sigma bonds with their respective alkoxy groups. This can also be used here. So you can see here with this reaction that we have this 1,2-ethane diol right here, 1,2-ethane diol, and we're reacting it with acetone. And so this is the simplest of the ketones. And you can see that in the end, we have an O R group right here, right? We have an O R group. And right here, we have an O R group. So it looks just like ROH, and on this side, it looks like ROH. And so in the end, I know that I should attach an O with this guy on one side and then an O with this guy on the other side. And you can see through the mechanism that in fact we did attach it like so. And so this is how we can form a cyclic acetal. In fact, it is a derivative of the blocking group, okay? So we can prevent chemistry from happening to a special carbonyl group, okay, if we give it this hat. Okay, so I'm going to call this the acetal hat from now on, okay? So we can give something this 1,2-ethane diol treatment and it gets a new hairstyle. And once it has this new hairstyle, you can't really do anything to it, okay? In addition, if you simply just put it in water in an acidic environment, so that is namely hydronium, it will reverse the reaction and give you back the carbonyl. Okay, so we have a way to attach this hat to block chemistry from happening at this position, and then we also have a way to simply remove the hat and get back the ketone that we wanted. So we're going to go ahead and now apply what we just learned to this molecule. So let's make some observations. I can clearly see that we have a ketone here and we have an ester at this right side. So we have an ester right here and we have a ketone right here. The ketone remains on this molecule, but the ester has been reduced to an alcohol, interestingly enough. So at this carbon, it got reduced to an alcohol, okay? Now, here's what I do know. Clearly a reduction happened in this reaction, but let's see if we can work this out. So I'm going to redraw this on my paper, and let's attempt to work out this problem. So we have this molecule. I believe I drew this correctly, where R is just some carbon group. And we need to somehow turn it into this guy. Let me just write this in a more formal way. So we need to get him to there. Well, if I used, let's say, sodium borohydride, it's a reduction reaction. Well, if I had used sodium borohydride as a reducing agent and then put it in some water, so I have some water workup, I'm going to get this as my product. I'm just going to get this guy reacting and the ester did not. So clearly, this is not going to work. I can't use that reduction reaction. Well, what about if I used lithium aluminum hydride, Sammy? So we try and use lithium aluminum hydride this time because lithium aluminum hydride can reduce esters. So let's try that and see what we get. Might as well put it down and see what we get here. And interestingly enough, it gives us something very, very close to our product, but it doesn't exactly give us what we want. We get this diol product. And so you see that we run into this problem. We only want to reduce this ester. We do not want to reduce this ketone. So what do, right? Well, we have just learned about this new trick of ours, which is putting on a hat, right? If we put on that hat, then what we can do is prevent chemistry from happening at that position. So allow me to write this on another page, and we're going to go over what that chemistry is exactly. So let's say that I have my starting molecule, which is this. And I'm going to put a hat on him, okay? So I'm going to react him with this 1,2-ethane diol, and that of course is in an acidic environment, okay? And I'm going to go ahead and put a hat on there. Now, this is very, very important to recognize, but the hat only attaches itself to ketones and aldehydes. It does not work with esters or carboxylic acids. So the ester here is completely untouched. Okay, I'll say that one more time. This hat does not work with the carboxylic acids or the esters. Okay, so we get this as our product. Now, if I was to use a reducing agent, one suitable for reducing an ester, which is lithium aluminum hydride, I only reduce the ester group. I can't reduce these ethers, right? I cannot reduce these ethers or this acetal group in general. They can't be reduced. So I use lithium aluminum hydride to reduce that ester group. In the process, I get the following. It's at this point that we've recognized that we're so close to our end product. We just need this acetal to turn back into a carbonyl. And we know how to do that. We saw on the slide just now that if we put this in hydronium, namely water in an acidic environment, okay, we will return back our ketone. So we put water in an acidic environment and we get back that ketone. So if you only want to touch one of the groups, you only want to do chemistry to one of the groups, simply block the other one. And so we have now gotten to our product that we wanted. Okay, so this is very, very useful in synthesis and in general organic chemistry's late exams. Okay, so let's return back to the PowerPoint now. So now we know how to use blocking groups. Clearly very, very useful. Okay, and here's just a summary of those such reactions. The only difference between mine and theirs is that the second step of a lithium aluminum hydride, which is their third step here, instead of putting it in water like I did, you could put it in hydronium, and you could protonate the alkoxide ion, and at the same time you can also get rid of the hat. Okay. So I'm going to give you some time to do these ones. Pause the video now if you would not like to see the answers. But go ahead and try these ones on your own, and we'll work them out, okay? And I'll walk you through them. Okay, so let's go ahead and work through these such problems. Okay, so we want to do some chemistry here. And I have this cyclopentane parent hat looking guy, and I put him in hydronium, right? So that is, right, the same thing as water in an acidic environment. They're the same thing. Same thing. And I know that whenever I put these OR groups in hydronium, I return back my carbonyl. Okay? So I get this. I just get that carbonyl back. So this carbon center is the only carbon center that was involved in useful chemistry. Okay, well let's look at another example. Say that I have this cyclobutane derivative, which has OCH3s, or I'm labeled them here as OMEs. So there are two alkoxy groups, and they are methoxy alkoxy groups. And I'm going to play the same game. I'm going to put it in hydronium. Okay, I'm going to put it in hydronium. That is water in an acidic environment. And of course, very trivially, we simply form cyclobutanone. Okay, cyclobutanone. So clearly these are not very difficult reactions. But let's look at this last one on our list. So those two weren't so bad, you might say. But let's look at this one. We have an OH right here, and we have a ketone on the other side of the molecule. And it just says, no water, I'm just putting this guy in an acidic environment. Okay? So you may be thinking to yourself, that's a little strange. I honestly don't know what to do, Sammy. Well, this is where you need to begin to train your eye in organic chemistry, but recognize that this looks just like an HOR group, right? It looks like the ROH group, where this is the H, right? This is your H, this is the O, and then your R group is everything on this side. And so this is really functioning as the attachment for this guy right there, correct? So what could that be? So I'll give you another minute. Go ahead and look at that one and see if you can draw the answer for it. Okay, so let's go ahead and try and do this one. What I do know is that, and maybe Klein should have specified it more here, but I know that this O is going to attack this carbon center. So let me say that again. This oxygen is going to get protonated and it will protonate the carbonyl. It will then, this oxygen, attack this carbon center right here, and it resonates up the pi bond, so it's going to attach itself right there. That's all I do know. So we got to make a ring. So let me go ahead and make the ring first. So let's see here. We have 1, 2, 3, 4, 5. So we have, again, 1, 2, 3, 4, 5 carbons in the ring. And then we have a sixth point in our vertex, which is an oxygen. So we have a six-membered ring with an oxygen serving as one of the points. So that would give me this. Again, 1, 2, 3, 4, 5, 6. And allow me to label them in case you get confused. But I'll label the oxygen as point 1. This is 2, 3, 4, 5, and 6. That is where my ring is going to be. So allow me to label this again as 1, 2, 3, 4, 5, 6. And I can clearly see that at the sixth carbon, there's a methyl sticking out. So there it is. And then I also recognize that at the sixth position, because this is going to form a hemiacetal product, I need an OH also at the sixth position, right? A hemiacetal has an OH on one side, right? A hemiacetal has an OH on one side, and then it has the OR group on the other. So here's the sixth carbon. It has an OH on one side, and then an OR group on the other side. So there is my OH, and this is a hemiacetal product. Okay, so this is an intramolecular hemiacetal reaction, and we form this product in the process. Okay, let's go ahead and move back to our PowerPoint. And we see here that this is the hemiacetal. This is a new functional group that you need to remember. A hydroxy group on one side and an alkoxy on the other. Okay. Now, hemiacetals are quite difficult to isolate, and so you typically end up with the acetal product. However, for our prior example, okay, we did not really have two equivalents of this starting reagent, nor did we really have anything else that we could attach it to. So I knew that we were going to get a hemiacetal product on this one. Okay, so play around with that and come at yourself. So what's the simple formula here? Methanol, ethanol, propanol, put it in an acidic environment, and you form the acetal. Okay, now let us begin to look at an analog of that reaction. And what it is I'm going to put a primary amine, okay, a primary amine in an acidic environment. We're going to lose water at some point in the reaction, okay, just like our prior reactions, but I'm going to put a primary amine in an acidic environment. Hint, hint, that means that this guy gets protonated. And I'm going to lose water, but none of this stuff really matters. Just look at your starting product, which is benzaldehyde, and then look at your final product. It's this nitrogen, has a double bond, there's an invisible lone pair on the nitrogen, and it has a CH3 attaching outwards from it. So what is important to note here? What is important is that after all is said and done, what changed in this reaction is that this oxygen was substituted by an NCH3, an NCH3. So it's as if the hydrogens kind of just dropped out, and all I attached was this part right here. All I did was attach the NCH3 in place of the oxygen right here, right? So this is kind of interesting. I wonder how that mechanism works, okay? So this is just a partial explanation, but it says in mildly acidic conditions, which is this bracket H plus symbology, an aldehyde or ketone will react with a primary amine to form and I'm going to probably say this different ways, but I'm going to call this an imine, so that you know it. This is an imine, or imine, but imine sounds more suggestive. So this is an imine. So, okay, the arrow mechanism looks pretty scary. There's a lot to look at here, but let's sort of just take this step by step. Nitrogen is going to be acting as some sort of nucleophile in this, right? And it attacks that region of partial positive character. In the process, it does a bunch of stuff, but this is for you to study. This stuff is mostly useless, though. What do we care about? All that I cared about is that no matter what this was, all that I attached at the end of the reaction was N and the R group. N and the R group, okay? And of course as that one lone pair. So this is referred to as an imine or imine, and then we have this intermediate, which is like the hemiacetal analog, hydroxy on one side, and then the NR with an H on the other side, okay? So we call this a carbenolamine, okay? Carbenolamine. And then we have our imine or the imine as our product. So just remember that. NR is what gets attached. Okay, you can do this. Go ahead and pause the video, try and do every single one of these problems, and I promise you, it's not hard. All that you need to remember is that you simply, in replacement of that oxygen, you attach an N and its R group, okay? So go ahead and try that now, and then we'll go over it. Okay, so let's go ahead and go over these reactions. So for my first reaction, I have this benzophenone derivative, which doesn't really have the benzenes, but they're like cyclohexone derivatives. And it's this. Now I'm going to react him with MENH2. Now this TSOH, okay, toluene sulfonic acid, just think of this guy as really being him, okay? Just think of him as being that guy. And we have an MENH2, and we lose water. Doesn't really matter. Who cares? What's important here? What's important is that you need to just be able to recognize what the nitrogen and the R group are. And that is invariably this part of our reagent, correct? So my product will simply put the N at the oxygen and then attach a methyl to it. So my end product will be the following. N with a lone pair and the R group, which is in this case R equals methyl. That's it. It's that simple. So let's now look at the cyclobutanone. So we have this cyclobutanone molecule, and there it is. We're going to put it in an acidic environment, TSOH, and it's in brackets, so that's a new symbology that we've seen. And we are attaching ethylamine, ETNH2, and of course we dehydrate this molecule at some point. So what do? Simply just replace the oxygen with NET. Namely, you will end up with this as your product, N-ethyl. That is it. okay? Which is, of course, the same thing as this, okay, for those that need to see it. Just an ethyl group. That's it. So we have this way of forming the imine products, the amine products, okay? This imine, okay? All these are imines. And I guess, to make it easy, the I in imines, right? I is like a singular thing. It's like I and I only. So you can think of that I as only having one R group coming off of the nitrogen. So that's a good way to remember this kind of functional group. Okay, let's look at the other four reactions now. We have this cyclo heptanone molecule. So that's a 7-membered ring, and I'm putting amine, just NH3, okay, in an acidic environment. There it is. And of course, I lose water at some point. Now, this is a little strange, Sammy. You say, I know that we must get this as our product, an N, and then there's an R group. But what is that R group exactly? Well, you see that we have NH2 and then we have an H. So allow me to write this in a more suggestive manner, but allow me to write it as H-NH2, just like that. Well, what this suggests is that this is my R group right there. And so my product is simply this. Not too bad, right? Nothing tricky about that, okay? But that is my product, okay? Basically, every hydrogen, okay, is going to get rid of one of the bonds to oxygen, and this will be like some sort of diol derivative, and so the first hydrogen takes the place of one of the OHs, and then the other hydrogen takes the place of the other OH group, right, in that halfway house form. Okay, good. Let's now look at B. So this one was A. Let's now look at B. And we have cyclopentanone. Okay, you should know how to name these by now. And we have this cyclopentane parent amine derivative. So it looks like this. We are clearly putting this in an acidic environment. And we are having this loss of water, this dehydration at some point. So what is your N and what is the R? This is the N, and then this is the whole R group in red. Okay? Just like up here. That's your N, this is your R. That's your N, this is your R, that's your N, this is your R. Simply just identify those things. So your product is going to be, and this one will look kind of interesting, but you have this N single bonded to this cyclopentane. And that's your product. Okay, good. Not too bad, right? You're simply just attaching the N and the R group. So it gets kind of repetitive, but we also have some really interesting examples of this. So in C and D, this is clearly demonstrated, but we have some kind of intramolecular reaction going on here. So let's try and make sense of it, okay? So we have this, and it says, I'm not going to react it with any other molecule. I'm just going to put that molecule itself in an acidic environment. At some point, I lose water. Okay, well, you know that you must identify the N and the R group and replace that on the oxygen. So here's my N. Here is my R group, okay? It's all of that, okay? And I know that this nitrogen is going to replace that oxygen. So it's like we're going to have a ring, right? So allow me to write it like this, and I'll explicitly show this hydrogen, okay? I know I'm going to have the double bond N. I know that as a matter of fact. And this molecule, right, is going to at some point connect like that, right? The nitrogen is, this whole molecule is sort of just going to curl like this, and it's going to land on top of that oxygen. And so it's going to make a ring. That's what's going to happen. The nitrogen sort of reaches up, kicks off the oxygen, and it replaces itself right there. Right? That's the overall sum of what's going on. And so how big do I make the ring? This is how big you make the ring, okay? You know that your ring only consists of whatever is in red here, okay? So it's going to consist of a nitrogen, and then 1, 2, 3, 4 carbons. So 4 carbons and a nitrogen. That's 5 things. So I will have a 5-membered ring. You can see that this is 1, 2, 3, 4, and then the nitrogen. And you can also see that this is 1, 2, 3, 4. And you can see that 4 is matching up with where the double bond starts. So this is your product. So you've now been able to form a cyclic product. Okay? Cool. Now let's look at D. Okay, so let's look at D. And it's the same exact molecule, except we have a CH3 at the end. And at this carbon, we have 2 methyls. So you already know, okay, that we're going to get more or less the same cyclic product, but there's just different attachments. So we're going to get the same cyclic product. You know that. Drew that kind of ugly. But allow me to write this as 1, 2, 3, 4. And I know that at the 4th carbon, okay, which is where the double bond O or the double bond N starts, this 4th carbon, I have a CH3 that attaches. So here's the 4th carbon, there's my CH3 that attaches. And then if I go from the 4th carbon, I go 1, 2 over, I'll have this dimethyl. So if I go 1, 2, I have a dimethyl. Okay? 1, 2, I have a dimethyl. That is your product. Okay, good. So clearly all you have to be able to do here is identify the nitrogen that is reacting and then the respective R group in order to form your imine or your amine product. Okay, good. Let's continue. There are other ways that you can also do this. What if the R group was replaced with the hydroxy group? So that is that you have a hydroxylamine reacting with the carbonyl, okay? Well, then you form this N R product, which we call an oxime. So you need to commit to memory a hydroxylamine, which is this guy, and you need to commit to memory the oxime functionality. In addition, we need to learn this new one, which is a hydrazone. Okay, so we use hydrazine, where NH2 is the H2 is the unreactive part, but the N to the R group is this whole NH2 right here. This guy is functioning as an R group. So we formed this dinitrogen product. Okay, the nitrogen single bonded to a nitrogen product. We call that a hydrazone. So this right here is called hydrazine, and we form a hydrazone product. And this is invariably an intermediate step in Wolff-Kishner reduction used to completely get rid of carbonyls, and we'll see that just momentarily. The products of these are completely trivial. It's simply just going to be NOH for this guy, and then it's going to be N to NH2 for this guy. That's it. Okay, good. So let's move on. We're getting right through real fast. So what about if you did not have 2 hydrogens? What about if you only had 1 hydrogen? That is that you had a secondary amine being represented by 2 R groups. Well, what we form now is not an imine, but we form an enamine, okay? You form an enamine. And so let's think about the differences here. I have an extra R group. I still have that invisible lone pair on the nitrogen, but there's no double bond here to the nitrogen. Instead, the double bond was really shifted down an extra carbon bond. It's kind of interesting. So secondary amines only formed the one bond to nitrogen. Surely, and certainly, it's in the place of the oxygen. So we lost a pi bond, but we replaced it with the Nr2 in the end. Interesting. So let's go ahead and look at this. And again, we still lost water. We still have our acidic environment. It's just a secondary amine now. So in acidic conditions, an aldehyde or ketone will react with the secondary amine to form an enamine. Okay? So, okay, a lot of this looks the same. We form the carbenolamine, and then we form whatever this is, right? We get the double bond, one more carbon over, and it only has a single bond to N. Now, why does this make so much sense to us, though? Okay, this makes so much sense because if you look at the imine up here, we can have the double bond to nitrogen, okay, with the lone pair because that gives it no charge. But if we had the double bond to nitrogen right here, okay, and we had a lone pair, that would be too many bonds to nitrogen, and so it would give it a charge. So Mother Nature, okay, reality, literally knows what to do. It says, I'm not going to form the double bond here. I'm only going to form a single bond and still keep the lone pair so that I have no charge around me. And it puts the double bond an extra carbon over. So the mechanisms are exactly the same, except at the last step, it's just about that different. It's the only difference is just the last step. You can see that the last step for the imine production is it rips off a hydrogen to get rid of the charge on nitrogen. Whereas here, it does this beta hydrogen elimination in an E2 kind of fashion, and you form the enamine product. Quite interesting chemistry there. Okay, so let's go ahead and work out this example. And I'm going to do it on my piece of paper, but I encourage you to just write down the product. You don't need to write any arrow mechanisms, just draw your product, okay? And we'll do that here in just a second. Okay, so we need to form this product. And what we start with is we start with cyclohexanone. So here it is, cyclohexanone. We're putting it in an acidic environment, okay? That's what the bracket sulfuric acid means. It's in an acidic environment. Who cares what symbology you want to use? But I know that I'm attaching a nitrogen with two ethyl groups. This is diethylamine right there. And of course, at some point, we lost water. So I know that my N with my two R groups is an N, and then it's two ethyl groups. So I know that I'm going to get a single bond to N with the two ethyl groups. I know that. But then you say, where does the double bond go? Well, it can't go attached to the nitrogen. It can't do that. But it can go either here, okay, or it can go there. It could go at either which one of those positions. And it's arbitrary. It doesn't matter. So I'm just going to choose that one. And so this is my enamine product. Simple. Not too bad. We can do that. So I'm now going to let you work out these examples. I can find my OBS. Okay. I'm going to let you work out these examples. Okay. Take a minute to pause the video and then come back and see if you have the correct answers. Okay. All right. So let's go ahead and go over these questions. There's 4 of them, and I hope that you got them all. So we have this Cyclo Heptanone once again. I hate drawing 7-membered rings, but there's my Cyclo Heptanone. There he is. And I'm reacting him with this cyclic secondary amine molecule. So it's a 5-membered ring with a nitrogen. It's in an acidic environment. And I know that at some point I lose water. Okay. I need to replace this oxygen with an N and its 2 R groups. So you can see that the 2 R groups, right, one goes this direction and the other one goes that direction, right? So that's 2 R groups. That does classify as it. So simply redraw your 7-membered ring and put your 2 R groups in there, which is that. Of course, it does have a lone pair. I'll explicitly draw it there. And you know the double bond's got to go at either the left side or the right side. It doesn't matter, so I'll just put it here on the left side. And there's my enamine product. Okay, let's move on. Let's now look at B. Say that we have this as our starting product. So we have this nitrogen, and it's got 2 R groups, certainly large R groups, but they are 2 R groups, cyclohexanes. And then we have this cyclopentanone. We have cyclopentanone in an acidic environment, and we lose water. Okay, first step. What is my N? What are the 2 R groups? There's my N, and here are my 2 R groups right here, right? So let's just replace that oxygen with the N and its 2 R groups and make this a single bond, make one of these things a double bond. Okay, so here we go. Replace this with the nitrogen and its 2 R groups. Okay. It's kind of strange to draw these because they're so big. But there's N and its 2 R groups. And then we put a double bond at one at the left or the right side there. That's it. So there's your product. Hope you got that one too. Let's look at C now. And we have quite a interesting molecule here. But it looks like we're doing some intramolecular work. That's probably what you're thinking. Sammy, we're doing some intramolecular kind of move here. But it's just the same game that we've been playing. Okay, you've got this. So you know that this nitrogen is gonna take the place of that oxygen. In the process, this will become a single bond. So we already know that this is gonna wrap around and form a ring. That is obvious. But we need to know, is it a 6-membered ring, a 7-membered ring, right? How many vertices does this ring have? Well, nitrogen, okay, is going to clearly attach itself there, and so from that oxygen to the nitrogen, that will constitute how many vertices in the ring we have. So nitrogen, let's just call it our first position, okay? So imagine the nitrogen being the first position, and it's right here. The next position over, okay, and allow me to call this nitrogen, okay, but we're going to have 1 right here. This is 2, 3, 4, 5. So we have another 5-membered ring, okay? So allow me to draw it like this. So here's 2. And I know I have the single bond N. Now, this is of course my first position in the ring. I gave it a 1 as I did right there. At the first position, I have a methyl that extends outwards. Okay, I'm going to go ahead and do that then. There's my methyl. So again, at the first position, attached to my nitrogen, first position which I've called nitrogen, I have a methyl. There it is. That chicken foot ending stays the same, and I have the single bond N1. Now, I need to make a 5-membered ring as I stated, and so I'm going to just draw it like so, just make it 5-membered. There it is, where this is going to be 3, 4, and 5. And I can see now that I have to put a double bond, right, either here or here. So you tell me, can I put it on this left side? Well, no, I can't put it on the left side because that would break the octet rule. I can't do that. Okay, but I can surely put it right there. So I put my double bond right there. And this is my intramolecular enamine end product. Good. So if you got that, good job. And we have one more example to go over. Okay. So now we have this such molecule. It is a benzene derivative, and we got our ketone in there. Excellent. We have this dimethyl, and we have this N with two R groups, and it's in an acidic environment. We lose water. So go ahead and try this one, okay? But we're going to play the same exact game here. I know that from this point to the nitrogen, that will constitute what membered ring I have, okay? So here's where my nitrogen starts, and I can see that there's an R group right here that moves in that direction. It's only 2 carbons long, okay? But I'm only interested in the R group that connects to where my nitrogen is also attacking. So allow me to call this oxygen my first position, which is really the nitrogen, right? Because the nitrogen is going to wrap around to the oxygen and take its spot. So the nitrogen is my first position right here. So I'm going to call that 1. Then I'm going to count down, and I'm going to call this my second position. And then I'm just going to keep on numbering. 3, 4, 5. Well, we have a 5-membered ring. So what was not touched? This benzene wasn't touched, so I'm just going to redraw it right here. And once I go over 1 carbon, right, I go over 1 carbon, I hit my second one, and then I make my 5-membered ring. So make your 5-membered ring. Be sure not to put the double bond to the nitrogen. I'll number everything accordingly like I have been. And I'll say, well, at the first position, which I've called nitrogen, I still have this ethyl that I need to attach to him. So here is the ethyl. And I know that from this position, either to the left or the right, I have to put a double bond. And I cannot put a double bond right here because that would break the octet rule. Carbon right here already has its 4 connections. So I've got to put it on the right side here. So I put it right there. At the 4th carbon, there's also 2 methyls. And so there they are. This is my enamine product. And that's it. That is how you work out all of those such problems. So I hope you got them all right. Okay. Okay, so we've just passed over an hour, so I'll briefly speak on this, but I talked about Wolff-Kishner reduction. We've used it in the past, in fact, okay? But now here you fully will know how to do the mechanism. So if you start with a ketone, okay, and you put it in hydrazine, okay, it's one of the NH2R derivatives, you form this imine derivative, okay, and that can then itself be reduced completely to just a hydrocarbon chain, okay? So you put it in this very basic environment, heat to drive the reaction forward. There is the arrow mechanism for it, if you're interested in looking, and you just end up reducing the carbonyl completely, okay? Just reduce that carbonyl completely, okay? These are practice problems for you. I encourage you to try them, and if you would like the answers, just please email me. We're about to hit an hour and 10 minutes, so that's probably a good stopping point for this video, but you definitely got a lot done, and you know a lot more chemistry than you didn't. So, cheers.